In class, we talked about history and the way people perceive things as part of a way to look at environmental science. The other way to look at it is the scientific perspective, and they use something called systems. Systems should sound very familiar because it's the very basic things like ecosystems, and that's really where we're getting a lot of our terminology from. You hear the word system a lot, you just don't think of it as defining the way we do. So 1.1.1 is actually to have you guys define what a system is. So a system, when you're defining it on your exam, is an assemblage of parts working together to function as a whole. And a system, like we said, it could be an ecosystem. But you really have to remember we're a half history course. So it could be the legal system, the financial system. Ooh. Sorry, that got crazy there. I apologize. The bureaucratic system and social systems. And we talked about one in class on Friday, which was our value system. So you can't really think of it as science-y because it's just a way to perceive the world around us and how to understand how moving parts come together to work together as one piece. And 1.1.2 is for you guys to see not only the range of systems we can have in kind of types, but also in size. So we can go small, 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 like a drop of water, to looking at the whole globe as a system. And I'm going to try and draw the Earth. That's not too bad. And you can even get any bigger and think of the whole cosmos as a system. And of course, the bigger you get, the more working parts you have. In terms of systems, and specifically for ecosystems for us, the more moving parts you have, or the more inputs and outputs, is going to be the more stable system. The reason for that is it can bounce back from changes a lot easier. It has more options to bounce back. And this is really big when we talk about things like loss of biodiversity, and why it's important is when you look at it at a system, you really see that once you take that piece out, everything falls apart because there's not enough to balance out that negativity. When you look at a system, there are 3 parts or 4 parts. There's inputs, which is something going in. There's storages, which is what stuff goes into, and they're represented by a box. There's flows, so it's things moving through a system, and of course there's outputs. And they are modeled just like I did here, with arrows, with boxes, with things enclosed. And the general rule for systems at all times, and I'm telling you they put questions like this every year, is inputs always equal outputs. We'll talk about that more in class about why with the laws of thermodynamics, because it is a little bit complicated to get your brain wrapped around it. But this for right now is our general rule. Inputs will always equal outputs. Now, in terms of systems, there's one big example you need to know as a philosophy. So James Lovelock, he's kind of this first guy to kind of put the history and the science together in terms of looking at the world. And he called it the Gaia hypothesis, or the Gaia model. And he said the Earth is a living thing. And he said earlier the Earth was alive and it was able to bounce back using negative feedback. And we'll talk about more of what that is in class. And that was then. And he said now the Earth is kind of like a middle-aged woman. Oops. And she can't bounce back anymore. So she's sick, and she can't bounce back from the pollution, change in temperature. And because of that, we're no longer going to go back to our equilibrium, our happy temperature. We're going to find a new, warmer equilibrium. And that's because we've pushed the Earth too far and we've made the Earth sick. We will talk more about Gaia. It comes up a lot. And essentially this James Lovelock guy, he sounds like crazy when you read his article because he talks about the Earth as a living thing. But when you read it the way he writes it, and we'll have a chance to read it in class hopefully, you really start to think of as like, wow, it can't filter out all this poison we're putting in the Earth, just like our liver can't filter out all our poison once we push it too far. And it is very, very interesting. The next thing I want to look at is we've looked at what a system is, how people use a system. There are different types of systems. And this is topic 1.1.3. And I apologize for not explaining this earlier. When I write this, this is the assessment statement. And when you check your ESS handbook, you'll see them all typed out by number. And there are 3 different types of systems. Our first one is open system. And all that means it exchanges matter and energy. Be careful with your wording for this. Please use the word exchanges because some people use transfer, which is defined differently for IB environmental science. So it exchanges matter and energy. An example for that is, say I have a lake. All right, so the sun is putting in, this is a sun, guys, is putting in energy. But you still have matter coming in through things like runoff. And it evaporates water, so that's matter leaving. It makes food, so that's energy leaving. So it really is constantly exchanging matter and energy. Any ecosystem, any living thing is going to be an open system. A closed system has to be purposely made. It's not really found in nature. A closed system would be something like a terrarium. So I'm going to draw one of the terrariums I have on my window. So it's closed off. So this is my plant in here. And it's happy, but it still is getting energy. But it doesn't exchange any matter. So when we do a closed system, it exchanges energy. But not matter. And of course it gets energy through sunlight. Oops. Sun, I apologize. All right, and our next one doesn't really exist, is an isolated system. And it does not exchange anything. So it exchanges neither, energy nor matter. At first I thought the world was an isolated system, and then I realized meteors hit the Earth and the sun, we get energy from the sun, so that's an open system. The only one known in existence is the entire cosmos. So we're assuming that nothing else is coming in and out of our cosmos coming out of our solar system. Our next topic that we're going to talk about is we're actually going to skip a few assessment statements. Is we're going to do 1.1.7, which is the idea of when we look at flows, they can be classified as either a transfer or a transformation. And I would make a double bubble map, but it's hard with this pen. So I'm just going to make a T chart. So a transfer is just what you think about. If I transfer money into your account, it is still money. It's not changing at all. So that's the idea is it's like the movement of food through an organism. So things like fiber. Fiber goes in and then it comes right back out, folks. So fiber has not changed as it goes through your body, but it has transferred and has moved through you. It could also be things like non-living movement, things like runoff. Although runoff has gone from our farms to our lakes, it's still water. It hasn't changed at all. And it can also be movement of energy, but be careful with this one. It's the same energy. So it's like the ocean currents bringing in warm water. It's just traveled with it. It hasn't changed. It hasn't moved at all. Transformations is like transformers, all right? You're going from two different things, like car to robot. And that's when I go from matter to new matter. So when a plant does photosynthesis and then takes the glucose it makes and turns it into starch, turns it into cellulose to build that plant, that is a transformation. The next one I have is things like energy to energy. That's things like the sun coming into my car, but it's really turning into heat. So there are two different kinds of energy, and of course we have energy to matter. And those are things like photosynthesis. The sun is hitting the plant and is then creating glucose. The very last thing I want to do is talk about flows, inputs, and outputs in an example. We're going to be building a system in class, so here is my example. Are you ready? This is me. Let's talk about me as a system and inputs and outputs. So let's do my favorite food. So I love pizza. So pizza would be an input. Okay. Now I'm going to take that pizza and I'm going to store the energy as fat. But I'm also going to lose some of that energy. I'm going to use it. So some of it will be lost as heat, kinetic energy, growth, any kind of bodily function I have. I'm going to lose some of the pizza, of course, through digestion. And that's a very, very basic system. I have a storage, which is the fat with my energy. So I have transferred some of the glucose into fat to store it. I've transferred the energy that was stored in glucose and I've transformed it into heat, kinetic energy, and growth. And I've just transferred some of that fiber that was in my pizza through digestion. And so that's kind of the sum up for our video. You do need to be able to kind of do this and understand it. And I think I made a typo when I said I transfer things into fat. I transform glucose into fat storage. Although it's storing energy, they're two new molecules. So because I've changed it, it is now a transformation. And that's the end of our video. I apologize it's a little long, but I will see you guys Thursday, and there'll be a short quiz on this when you get into class.